In today's class, we will be studying about this chapter machines. It's the third chapter of this unit on mechanics. So, what does the word machine mean, or how did it originate? The word machine, it is derived from a Latin word, machina, and that in turn is derived from the Greek word mechain. Now, I may be pronouncing this wrong, but if it is to be pronounced as per the English pronunciation, it's something like mechain. So, does this word mechain or machine? What does it mean? It basically means an assembly of certain parts and portions, each of which has got its specific function, all of which work together to accomplish a task. So that's what machine is. But in general terms, as per what we understand from our daily life, machine basically means anything that makes our work easier. That's a machine. Anything that makes our work easier. It can be a pair of scissors, it can be a knife with which we cut something in the kitchen, it can be the bicycle on which we ride. So any simple device that makes our work easier is a machine, of which levers, which we shall be discussing shortly, are the most common type of, or the most simplest type of machine. So what are the functions of machine? Why do we need them in our daily life? Well, machines at times they help us to lift heavy load by applying a small effort. So if we are trying to lift something which is beyond our capacity, something very heavy, machines help us to lift it. One of the examples or machines that help us to do this is a spade. Similarly, a crowbar. These are certain machines that help us to lift heavy load. Another application of a machine is that it allows us to change the point of application and the direction of effort. So point of application of the effort and the direction of effort to our convenience. Where do we make an application of this particular advantage of the machine? Well, it is used in the simple pulley. Again, simple pulley you will be doing later on. So in simple pulley, we want to change the direction in which we pull the bucket or we pull the rope to such a direction which is convenient for us, and there the pulley, which is again a simple machine, helps us to change this direction and point of application of effort as we want it to be. And finally, machines help us to obtain a gain in speed. Certain machines which help us to obtain a gain in speed, or example is a scissors. The scissors with which we do our art and craft work, they have very long blades. The utility of the long blade is that they can move faster through the paper and allow us to cut it more easily. So this is what the word machine means and why we need a machine generally in our daily life. What are the functions of a machine? So then if you are asked to define machine, how do you define it? Well, a machine is a device as per your book. You have to write this definition so that you don't miss the keywords. A machine is a device with which we can overcome a large resistive force at some point by applying a small force or effort at a convenient point and in a direction by which we can obtain a gain in speed. So when you watch this portion, refer to your book. I am repeating the definition again. A machine is a device with which we can either overcome a large resistive force or load at some point by applying a small force or effort at a convenient point and in a desired direction, or by which we can obtain a gain in speed. So that is how machines are defined. Now, once we study machine, we need to know about certain terms. What is the term load? So load is basically this resisting or the opposing force that we are trying to overcome, that is load. And what is effort? Effort is the amount of force that we apply on the machine so that it can lift this load or resist this opposing force. The ratio of the load to effort is called mechanical advantage. So what is mechanical advantage? It is the ratio of the load to the effort. And similarly, there is another term which is known as velocity ratio, and velocity ratio is the ratio of the velocity of effort to the velocity of load. The word ratio is already in the terminology, and also you can find velocity here. So quite obviously it is the ratio of the velocity of effort by velocity of load. Now we know this, that velocity, any kind of velocity, is displacement by time taken. Therefore, velocity of effort can be written as displacement of effort by the time taken. So we can write velocity of effort to be displacement of effort by time, and similarly we can write velocity of load to be displacement of load by time. So from there, V by VL becomes dE by dL, the T cancels. So velocity ratio can also be defined as the ratio of the displacement of effort to the displacement of load. Now based on what are the values of mechanical advantage and velocity ratio, you can determine whether a machine will act as a force multiplier or speed multiplier, or simply be used to change the direction. Now if you find that the mechanical advantage is greater than 1 or velocity ratio is greater than 1, that means that particular machine has a utility as a force multiplier. So mechanical advantage greater than 1 means the ratio load by effort is greater than 1, and whenever a fraction is greater than 1, it implies that the numerator is greater than the denominator. So whenever I say that a machine has a mechanical advantage greater than 1, it means that with a small effort the machine can lift or overcome a greater load, and therefore those machines are force multipliers. It's like you apply a force of 10 Newton and the machine can lift a load of 50 Newton. So the machine works as a force multiplier. It multiplies your effort by 5 times so that the load can be lifted, hence this name. And if the opposite happens, like if to lift a smaller load you need to provide a greater effort, then the mechanical advantage is less than 1, because now denominator is greater than 1. You can write this out explicitly like mechanical advantage equal to load by effort less than 1, and a fraction is less than 1 when the numerator is smaller than denominator. So that means to lift a smaller load or overcome a smaller resistive force, we need to apply a greater effort. So those kind of machines are called speed multipliers. So speed multipliers have this mechanical advantage less than 1. They also have the velocity ratios less than 1. Why? Why do speed multipliers have a velocity ratio less than 1? Well, velocity ratio means velocity of effort by velocity of load. So velocity ratio less than 1 implies that the velocity of the effort is lesser than the velocity of the load. So which basically means that the load is displaced more than the effort. Finally, if these ratios, both mechanical advantage and velocity ratio, has a value exactly equal to 1, well, in that case what we can say is that those particular machines are simply used to change the direction of the effort that we apply. For example, a simple pulley. In a simple pulley, when you will study it, we don't want to multiply our force, nor do we want to gain a speed. All we want is to change the direction in such a manner that we can apply the effort by virtue of our own body weight. So in those cases, the load is equal to the effort, hence the mechanical advantage is equal to 1. Similarly, velocity of effort is equal to velocity of load, and thus the velocity ratio is equal to 1. So having talked about effort and load, or the displacement of effort and displacement of load, the next obvious destination is work, because we already know this, that any kind of work is equal to force into displacement. So what is work input? That is the work that we do on the machine by virtue of our effort. So we are applying an effort on the machine to overcome the load. The work that we do in the process is work input, and the work which the machine does on the load due to our effort, that is the work output. There is another quantity. We are already familiar with mechanical advantage and velocity ratio. There's a third quantity, physical quantity, known as efficiency, which is the ratio of the work output to work input. Now since we have both work in the numerator as well as denominator, quite obviously efficiency has no units because the units on either side of the fraction gets cancelled. Now this is very important, and hence I have highlighted this. Whether a machine multiplies speed, that is a gain in speed, or whether it multiplies force, that is whether it acts as a force multiplier or a speed multiplier, total energy is always conserved. There is no reason to believe that energy is getting multiplied. Energy is not increased or decreased by a machine. Whether the machine is able to multiply force or not, whether it is able to gain speed or not, total energy that is provided to the machine during input is always equal to the total energy obtained from the machine during output. So work input is always equal to work output. Energy is not increased or decreased by a machine. But obviously there is a limitation, and that is this conservation of energy principle is only followed for an ideal machine where there is no resistive agent. In the presence of resistive agent, like if there is friction, or if the machine is working in the presence of air, or if the parts of the machine are not perfectly smooth and frictionless, in those cases there will be a loss of energy and work output will be smaller. So assuming that we are talking of an ideal machine, one having a 100% efficiency, what is this input energy? Well, input energy is input work. Energy and work are analogous, and input work is the input force. It is the work which is done by our effort. So it is equal to the force of effort, as we see here, multiplied with the displacement of point of application of effort. Alright. That is all about the input energy. And what is output energy? Output energy is equivalent to output work, and that is equal to the work which is done by the machine on the load, and which is equal to the weight of the load, or you can say the resistive force of the load, multiplied with the displacement of point of application of load. Ultimately both of them have got the same form which you studied in chapter 2, that work done is equal to force times displacement. Effort is also a force, weight is also a type of force, and the displacement is obviously there. Now if a machine is ideal, like if it is having 100% efficiency, there is like say no resistive forces, or the mediums are frictionless and so on, in those cases what will happen is the machine will be 100% efficient, as a result of which the input work will be equal to the output work. Now what is input work? That is equal to effort into displacement of effort, and output work is load into displacement of load. Now for 100% efficient machine we equate them and we write that efficiency is output work divided by input work. Quite obviously this is what it is, as we defined in the definition of efficiency. It's the ratio of the work output by work input. So work output is load into displacement of load divided by effort into displacement by effort. So I separate load by effort and then divide it by displacement of effort by displacement of load. Now this thing is my mechanical advantage and this thing is my velocity ratio. So we get this final form, that efficiency is the ratio of mechanical advantage to velocity ratio, or it can be written as mechanical advantage equal to velocity ratio into eta. This efficiency, this symbol is called eta. So this is the formula for a machine which has got 100% efficiency, or in other words a machine that's an ideal one. So for an ideal machine, since efficiency is equal to 1 or 100%, mechanical advantage is equal to velocity ratio. And what happens for an actual machine? What is an actual machine? Again, if you refer to your book, you shall find an actual machine is one in which the output energy is always less than the input energy. Why? Because the moving parts, they are not perfectly smooth, there is some friction. The string, if any is present in the machine, is not perfectly elastic. Different parts of the machine are not perfectly rigid, and finally the moving parts of the machine itself are not weightless. So you have to know these 4 points. In case it is asked that how an actual machine differs from an ideal machine, you need to mention the 4 points. So this is what happens for an ideal machine, and if it's an actual machine, for an actual machine, since efficiency is less than 1, from this fraction that we did previously, we can find out that the velocity ratio is always greater than the mechanical advantage. A thing to note here is that all these quantities, whether mechanical advantage, whether velocity ratio, whether eta, all of them are unitless, because all of them are ratio of the similar quantities. In eta, we have got mechanical advantage by velocity ratio. What is mechanical advantage? That is the ratio of load to effort, both of which are forces, so the Newton, the unit, gets cancelled. Velocity ratio is the ratio of velocities of effort and load. Again, in this case, on numerator as well as denominator, what we have is velocity, so same unit gets cancelled. And eta is the ratio of output work by input work, so work on both sides of the fraction, that is numerator and denominator, so that also gets cancelled. As a result, all of these three quantities are unitless. So that brings us to the next area, which is levers. So what is a lever? It's the most simple kind of machine that one can imagine of. It's basically a kind of a rigid, either straight or bent bar, which is capable of turning about a fixed axis. The point through which the axis passes, that remains constant in place, but the lever rotates about that axis. And a lever basically works on the principle of moments, which we did in chapter 1. And in this case, the principle of a lever, the one it follows, is that moment of load about the fulcrum is equal to moment of effort about the fulcrum. What is moment of load about fulcrum? It's load into load arm. And what is the moment of effort about fulcrum? That's effort into effort arm. Whereas this load arm basically means the distance between the fulcrum and the load. This distance is load arm. And effort arm means the distance between the effort and the fulcrum. That is got the special name of effort arm in the case of a lever. Actually, in the chapter 1, you basically did product of force and distance. This was your anti-clockwise moment, and this was the clockwise moment. Here, the special name of load arm and effort arm are given, and that is what is written here. The load into load arm provides the anti-clockwise moment, effort into effort arm provides clockwise moment. And since this works on the principle of moments, they should be equal to each other, that is, they should balance each other. And if you do the ratio, you find load by effort is effort arm by load arm. Now this was my mechanical advantage. So mechanical advantage is effort arm by load arm. This is the formula of mechanical advantage specifically for the case of a lever.